So dear students, today we are going to discuss about thermodynamic cycles. So in thermodynamics, we know about the cycle, the meaning of cycle. It's about involving of the various processes, combination of all the processes put together, we are saying as a cycle. In the series, in thermodynamic cycles, we are dealing with the first cycle is about Otto cycle. So we have various clarifications, and among the clarifications we have about air standard cycles. So in the title of air standard cycles we have about Otto cycle, diesel cycle, and then dual cycle, Brayton. So these are the few examples of air standard cycles, which means about these cycles are working under the medium of air. So we know that the air is in thermodynamics, we are dealing with ideal gas, we are taking as a medium of this cycle. So Otto cycle consists of various processes. It is illustrating in the diagram of pressure versus volume, and then temperature versus entropy. So this Otto cycle consists of four processes. So this is the diagrammatic representation of Otto cycle, which is describing in terms of pressure versus volume as well as temperature versus entropy. So now we are dealing with the process one by one. So the process 1 to 2. So it is about, we are describing a pressure and volume cycle, and air is initially compression will take place. It's about isentropic compression. So which means about compression means we are increasing the pressure as well as about reducing the volume. So if the pressure is increases, automatically we know the temperature will increase, right? In isentropic, entropy remains constant. So what are the characteristic changes happening during the process of 1 to 2? So pressure from 1 to 2, it's increased, then volume it's get decreased, and temperature it is in, this is a diagram illustrating with temperature versus entropy. So temperature from process 1 to 2 it is increased, whereas entropy remains same. It is about isentropic process, right? So now the process 2, process 2 to 3, the characteristic changes. It's about, in the process of 2 to 3, actually we are adding the heat into that air. So we said that air is a working medium. We are assuming that it's an ideal gas. So we are adding that heat into that system. So the process 2 to 3, the characteristic changes, pressure, it is about heat addition takes place, which means about heat supplied is actually happening in this process 2 to 3. The characteristic changes happen, the pressure is increases, volume is remains same. It is about V remains same. Heat is added at constant volume. So we have two options. We can maintain volume as constant as well as about pressure as constant. In this process, we are maintaining volume as constant. In that, we are adding the heat. So Qs at volume is constant. So pressure increases, volume is constant, temperature is obviously increased, entropy is also automatically increased. If heat is added, we know that entropy will increase. So in a mathematical aspect, we can get that value of Qs. Qs is about m into, it's a specific heat capacity at constant volume Cv, then the temperature difference of T3 minus T2. So this is actual characteristic changes happening in the process of 2 to 3. Now we are moving to process 3 to 4. So it is a process again, it is isentropic process, but now the gas is expanded. After getting the heat, the gas is expanded. So it is about isentropic expansion process. So now let's say about what are the characteristic changes happening about during the process of isentropic expansion. So pressure, so from process 3 to 4, pressure get drops. Volume, its expansion, volume is getting increased. And temperature, from 3 to 4, temperature is getting reduced. And it is isentropic process, we are maintaining entropy as same. Now bring to that process, next process, 4 to 1. So it is about heat rejection is actually takes place at constant volume process. Now the characteristic changes happening about the process 4 to 1, obviously pressure it's getting reduced, volume as said it is a constant volume process, temperature from 4 to 1, if pressure drops automatically temperature is also getting drops, we know that. So temperature getting reduced and entropy is also reduced. If heat is rejected from the system, the entropy is also getting reduced. Mathematically, we are getting that value of heat rejection. It's about m into Cv into the temperature involvement is about T4 minus T1. So this is about heat supplied or heat addition as well as heat rejection. So this is the thing. Now we are going to deal with the efficiency of the Otto cycle. As we know about the universal formula, efficiency is always, it's about output by input. So in the system, so let us assume this is about that engine or the cycle, we are supplying heat as input and some of the heat getting rejected. So this engine will convert the sufficient heat into work done. So whereas input is Qs, output is W, work done. Obviously we knowing about. So output is about work done, input is heat supplied. We know that W, work done, we can get the relationship with Qs minus Qr. It is about work done obviously. So efficiency of Otto cycle normally work done divided by Qs, which means about Qs minus Qr divided by Qs. So once we are substituting the value of Qs and Qr as we said, seen in the previous terms, we are getting it's about MCV T3 minus T2 minus MCV T4 minus T1 divided by MCV T3 minus T2. So while we are simplifying this, we will get the value of 1 minus T4 minus T1 divided by T3 minus T2. So whereas this is the efficiency of Otto cycle in terms of temperatures. So as of now, this is about the detailed conditions of the Otto cycle, which is under the topic of as standard cycle. Thank you.